chemical kinetics. Chemical kinetics is also known as rate of reaction. And the rate of a chemical reaction is the number of moles of reactants converted per unit time to product, or the number of product formed per unit time. That is rate of reaction. You see, actually, chemical kinetics or rate of reaction actually as a study focuses on two major things. One, the speed of a reaction, that is how fast or how slow a chemical reaction occurs. And number two, the details of all steps involved in the reaction. This second one is known as reaction mechanism. Well, we keep to our scope, and here we are considering just the speed of reaction. So if I talk about the chemical reaction under this study, maybe in advanced level we will need to include this actually, but for this level we're just taking the speed, how fast or how slow a chemical reaction occurs. And so you see, rate of reaction is actually change in concentration of either product or reactant per unit time, per time taken. That is rate of reaction, and it is measured in moles per dm cube per second. So let's consider this reaction and let's see how we can write rate of reaction. Actually, rate of reaction is actually equal to negative 1 over the coefficient of this substance A. Then change, this is change in concentration of substance A over change in time. This is concentration of A. So change in concentration of A over change in time. Now, why are we putting negative? Actually, it is because whenever you write rate of reaction and you use the concentration of reactants, this will always give you a negative value. Meaning that during the course of reaction, understand that the reactant decreases. So the concentration of reactant would keep reducing. So if you take your final concentration minus initial, you always get a negative value. So it's important to put a minus here to make rate of reaction positive, because rate of reaction is usually a positive value. Now, it's also equal to minus 1 over B change in concentration of substance B over change in time. And it's also equal to, now if you are using the product to write rate of reaction, it won't have a negative value. So this will simply be 1 over C without the minus, change in concentration of C over change in time. And that's because change in concentration of products would always be positive, because the final product is always bigger than the initial product. So, and it's also equal to 1 over D change in concentration of C, of D, sorry, over change in time. So that is how to do this actually. So this is how you find your rate of reaction. The other approach is to getting rate of reaction. But the second approach is based on experimental process. But we'll talk about that also. Example 1, write the rate expression for the following. So here we have two different equations. I want to write the rate expression for each of them actually. So to do this, let's take the first one, the A. For the A, rate of reaction is simply equal to, now this is minus, I would have said 1 over 1, but that will still give us 1, so no need of that. Change in concentration of 18 over change in time plus minus 1 over 3 change in concentration of oxygen gas over change in time, which is also equal to 1 over 2 change in concentration of carbon dioxide over time. Now take note now, the moment we start using the product, we didn't have to put negative any longer. This is not plus, so please, this is equal to, which is also equal to 1 over 2 also change in concentration of water or steam over change in time. So that's for the A of this. This is the rate of reaction. Now, for the B, our rate of reaction is simply equal to minus change in concentration of iodide ion over change in time, and minus change in concentration of isochlorate 1 ion over change in time, then which is also equal to, please, there is an equal to here before the minus, which is also equal to change in concentration of chloride ion over change in time, and is also equal to change in concentration of change in this over change in time. So that's how to write the rates of reaction. So we want to look at the rate law. You see, the rate of reaction can also be expressed using the rate law. And the rate law simply expresses the relationship between the rate of reaction to the rate constant and concentration of reactant raised to some power. I'm going to explain all of this now. Let's consider this equation. Now, the rate law states that rate of reaction is simply equal to the rate constant K, then the concentration of the reactant raised to some power X, reactant B raised to some power Y. So these are the reactants. So this is what the rate law. So you can say rate of reaction just simply R is equal to K, concentration of A. Why we're saying A? Because A is the reactant, A and B are the reactants. So concentration of A and concentration of B raised to some powers. That's what the rate law is saying. Now, there are some things to note about this rate law. You see, firstly is that you cannot express the rate of reaction. If you're using rate law, you cannot express it based on the concentration of the product. No, that's not possible. You cannot say K, concentration of C, concentration of D, raised to some powers, maybe X and Y or whatever power. You can't do that. You don't use concentration of products, but concentration of only reactants. That's one thing to note. So take note of that. Number two, that the rate law can only be obtained, or the rate equation can only be obtained experimentally. So note, the rate of reaction using the rate law cannot be expressed with or by the concentration of the products raised to some powers. So you can't do that. Another thing to note is another thing that it can only be obtained experimentally. So you can't get the rate equation just by theoretical method. You must carry out experiments on a particular reaction before you get the rate law for that reaction. Number 3 is that, you see, it is S order in A and white order in B. And also the overall order of the reaction is X plus white order. And so what this simply means is that, you see, we need to know the value, or we go get the value of X and Y, and then the K. The K is called the rate constant. And so, you see, let's assume that we have an equation where R is equal to K A raised to power 2 and let's say B raised to power 3. Now, this reaction is second order in A and third order in B. That's what we're trying to say, that it is S order in A. So whatever the power here is, that is, it is like here is second order. And the power here is 3, is third order in B, second order in A. Now, if you ask me what is the overall order of this reaction, it's simply 5. That's 2 plus 3. That is the overall order. So ways of measuring reaction rates. You see, the rate of reaction can be measured by any of the following means. 1, the rate at which the mass or concentration of reactants is decreasing. We all know that during a chemical reaction, the reactant is being converted to product. So definitely the reactant is decreasing. So you can use the rate at which the mass or concentration of reactant is decreasing to determine the rate of reaction. Again, the rate at which the mass or concentration of product is increasing, because definitely the product will be increasing. So the rate at which the mass or concentration of that product is increasing can be used to also measure the rate of reaction. Sometimes, if these two methods are not possible, you can also use the decrease in mass of reaction system. Maybe you're carrying this reaction in a container and one of the product form is a gas. The rate at which the gas is escaping, therefore, if the gas, once the gas starts escaping, the mass of the substance will be decreasing. So the decrease in mass of the reaction system, the entire system itself, due to the escape of maybe gaseous substance, can be used to measure the rate of reaction. Again, is that we can also use the volume of gaseous products formed to measure the rate of reaction. The amount of precipitate formed can also be used to measure the rate of reaction. Sometimes the change in pH can be used to measure rate of reaction. Again, change in color intensity. As reaction occurs, intensity of color varies, and we can use that to measure the rate of reaction. Also, change in total gas pressure can also be used to measure the rate of reaction. And lastly, time taken to arrive at a scene stage can also be used to measure the rate of reaction. The rate curve. You see, the rate curve is a graph that shows the rate of reaction. And the rate curve can be plotted using the concentration of the reactants against time, or using the concentration of products against time. Now, this is the rate of reaction using, this is how the curve looks like, using the concentration of products against time. And if we are using the concentration of reactants against time, the curve will look somewhat like this. And we can see that it's increasing here and almost no increase towards the end of the reaction. And it's decreasing here and almost zero towards the end of the reaction. That tells us that the rate curve simply shows us that towards the end of reaction, there's no increase or decrease in rate of reaction. It almost gets to zero. But at the beginning, there's a huge increase, telling us that the rate of reaction is fastest at the beginning of the reaction and slowest towards the end, or it leads towards the end of the reaction. Collision theory. The collision theory simply states that for a chemical reaction to occur, the reactant particles must collide with one another. This simply means that if there's no collision between the reactant particles or reactant particles, then chemical reaction cannot occur. Although we have so many of these collision, but not all of this collision results to chemical reaction. Even though the reactant particles collide, doesn't still mean that chemical reaction would take place. You see, for chemical reaction to take place, a certain amount of energy must, the reactant particles must possess a certain amount of energy before a chemical reaction can take place. This energy is known as the activation energy or energy barrier. So the activation energy is simply the minimum amount of energy the reacting or colliding particles must possess before a chemical reaction can take place.